Go ahead and get this going here. So let me read this problem. Let's kind of think about how we would do this. Okay, this one says to estimate a number of people in Springfield, population 10,000, so that's a given, who have a swimming pool in their backyard. 250 people were interviewed, and of those polled, 105 had a swimming pool. How many numbers do you see in this problem? First question. You see 3. Now what you're trying to find is you're trying to find how many people in the city would expect to have a swimming pool. So you're trying to find one number and you're given 3. A lot of times what that says to me is I've got a proportion of some sort going on. So what we have is this is like a total population. So let's just write down a couple of things. The total population is 10,000, so we have that. Okay, then it says out of those interviewed, we have a total of 250 were interviewed. And then it says out of that, that's kind of like a part. Out of that 250, it said 105 had a swimming pool, like that. So lots of times, not always, but if you got 3 numbers and you're trying to find a 4th number and they're being related to each other in some way, a lot of times you have a proportion. And a proportion you kind of look at, you're relating a part to a whole, is the way I look at it, okay, like that. So if I was to go through and do this, first of all, what you want to do is you want to go ahead and just set up 2 fractions equal to each other. That's what a proportion is, okay? An example of a proportion would be 1/2 equals 4/8. Everybody agree 4/8 and 1/2 are the same number? Okay. Well, 4/8 reduces to 1/2, but notice on this, if I cross multiply, I got 1 times 8 equals 2 times 4. So if you have a proportion, you can cross multiply. That's a guarantee. Okay, it always works that way. So what we're going to do on this is I'm going to put the whole on the bottom and I'm going to put the part on the top. I'm making that decision. You can do that backwards too. You can put the whole on the part and the bottom, but you want to be consistent. So once you make your decision, then you want to get that put together like that. All right. Well, let's look at what the totals are. The totals would be the whole. So what you could do on this is you could put the 10,000 there, or you could put it on the other side. And then the total people that were interviewed would be 250 like that. Okay? This is kind of like how a statistician would do a sample. Instead of going door by door to all 10,000 of these people and say, you got a pool? Okay, what you do is you do a sample. Okay, like out of 250, maybe you have a mail-in thing and they tell you. Okay, like that. So that would be the whole. Now, where does the 105 go? The 105 is a part, but which part of the fraction would it go on? The left one or the right one?
The right.
The right one, okay, logically, because that is related to that sample like that. Then your unknown's right there. So that's how you set it up. You've kind of got the part to the whole, 10,000 is the big whole, and then 250 is the smaller sample. Does that make sense to everybody? Okay? Now, since you have a proportion, and once you know it's a proportion, then you can cross multiply. So what we can do is we can multiply that times that. So you just write down 250 times x equals, and it's guaranteed to be equal to whatever 105 times 10,000 is equal to, like that. Okay, now that's going to be a super easy equation to solve. So we're going to have 250x here. Would you have to get your calculator out to do 105 times 10,000? You could, but what does that do? It just adds 4 zeros to 105, right? So I'm going to do 105, and I'm going to go 1, 2, 3, 4, like that. And that's what you would get, okay? Then what do you do to close off the problem? Divide by 250, good. Okay, so what we're going to do now, we're going to divide both sides by 250. Now I think it's pretty reasonable to get the calculator out, so I'm going to go ahead and do that. I'll pull up my calculator and see if I got that set up here, and let's do that. Okay, so let's see, 100, no, what was that, 10,000, no, what is that? Oh, it's 1,500,000 is what it is. So then I got 4 zeros. Sometimes I can't see this calculator very good. Okay, so I do that, and that will give me 4,200 people out of that total of 10,000 would have a pool. Okay, so that's the answer to the problem. Now, what you want to do on this is you want to understand why this is the right answer. Yes?
Couldn't you just divide 250 and 10,000 and just multiply that by 100?
That's what I just did.
Oh.
Okay? In a sense, that's what I did, right? And a lot of times students want to do these problems this way because you've probably been taught that in the past. You want to get an equation. The purpose of this is to set up an equation and solve the equation. But you're right. That's what I did anyway. Okay, so try to get an equation set up. Okay, now I'm going to teach you how to check this. And this is how you make sense of this. So what we have is 4,200 people out of 10,000 have a pool. Okay, that should be equal to 105 over 250. Now there's two ways to verify this. One way is on the calculator. Just think of a percentage. If you did 42,000 or 4,200 and divided that by 10,000 like this, so that's going to give you a decimal. It gives you 0.42. What percent does that mean? 42%. A little less than half have a pool. So if I did 105, and if I divided that by 250, then I hope I get 42%, and indeed I do. So hopefully that would help you understand the problem. That's what we did. Okay, is that clear? Okay, so proportions, that's how you do those. You tend to look for problems where you have three numbers given, you're trying to find the fourth, and there's a part to whole in there somehow. That's generally what you look at, okay? Okay, now this one right here you could do without a proportion, but I want you to go ahead, let's read this and I'll let you set it up and solve it. But I think this one is one that would be easy enough that you could just do simply, maybe even in your head. So one of the things that I know we use proportions for is if you go to a copy machine and you either shrink an image or expand an image, indirectly the math behind the scenes is doing a proportion, okay? So it's taking like a rectangle and either multiplying everything by a number or dividing it by a number if you're shrinking. So what this one says, you have a photograph that has a dimension of 3.8 inches and 2 inches like that. So let's draw a rectangle on that. So then it says we're going to increase the original 2-inch dimension to 4 dimensions. Now this one we're going to do with a proportion, but I want to see if you can tell me how you would do this, because this one is like, you can figure this out easy. What would you do? What's one way? Without even algebra. Multiply what by 2? Absolutely, right, okay. This thing's doubling, right? Therefore that's doubling, okay. So that would be one way to do it, but if we were going to do a proportion, we could do it like this. And you can set proportions up in all kinds of different ways. I'm going to just kind of keep doing part to whole. So the way I look at this is this number relates to that number. Okay, like that. Okay, the 2 relates to the 4, like that, right? Now go over here. Can you tell me what would go on the left side? 3.8 over what? There you go. Okay, part to whole. All right, does that make sense? Well, all you got to do is double 3.8 and you got the answer anyway. But you can't always see that, okay? This is just easy to see. So now what you do is cross multiply, so that would be 2x. Then you could do 3.8 times 4, like that. You can do that on your calculator. You can even divide by 2 now if you want to. So let's see, 3.8 times 4 is going to be 15.2. So we have 2x equals 15.2, and then what do you do to finish up this problem? Divide by 2. Good. Okay, solve the equation. So we undo that multiplication of 2 by dividing by 2. And what's that? 7.6, I think. Okay. Okay. All right. Okay, does that make sense to everybody? Okay, I'm not going to spend much time on proportions. Students generally in this class do pretty well with proportions. There's 2 other types of word problems we're going to look at that are a little more challenging. So we're going to go ahead and look at those. Any questions about what I just did then? Okay, all righty. Now we're going to do what we call a work problem. And in fact, all of the word problems in this section have something to do with equations that have fractions in it. That's the point behind that, okay? So let me kind of help you understand what's going on this. I recommend when you do these problems that you kind of put together a chart that will help you to put together your equation, okay? So let's read what this has, and I'll kind of show you how I sort through this and think through this. All right, so this says that a painter can finish painting a house in 7 hours. Now that's saying if he's doing the job by himself, okay? And there's nothing that slows him down, okay? We're just saying this job can be done in 7 hours. Okay, then has an assistant. The assistant maybe is learning how to paint, so it's a little slower. So the assistant can do this job a little slower in 9 hours, okay? So what's going to happen is they're going to work together. And let me ask you a simple question. If they work together, would it be logical, tell me this, would the amount of time if they work together be less than 7 hours or more than 7 hours? What would you expect?
Less.
I hope less, because that assistant's going to be getting in the way, right, or doing something to slow that guy down, right? So the answer to this problem, without a doubt, is less than 7, okay? So what we're going to do is we're going to fill in a couple of things to start with. So the painter alone, we're going to make just a chart on this. Okay, that's a given. That takes seven hours. Okay, the assistant working alone can take 8 hours. Together, we have no clue. So that's going to be our variable. That's going to be your X right there. Okay? What's that?
Oh, you said it was.
No, I got it. Okay, that's X or whatever variable you want to call that. Okay, now let's take a look at this. Well, let's see if this makes sense to you. Okay, before I do this, let me just say that let's say that you can do one job in 2 hours. This is a concept that I want you to get down. So if you can do a job in 2 hours, can you tell me what fractional part of the job would be done in 1 hour? Every time 2 hours goes by, you're done. When 1 hour goes by, how much of the job's done? A half. Logically, right? Half and then a half, like that. Okay, well, let's look at this, okay? If you can do one job in 7 hours, can you tell me what fractional part of the job is done in 1 hour? What? No. Okay, how about 1/7? 2/7, 3/7. Let's do this. 1/7, 2/7, 3/7, 4/7, 5/7, 6/7, 7/7. Job done, right? 7 hours has passed. Now, one way that you can reason this out, this is an equation. You can divide both sides by 7, and you get 1 hour is equal to 1/7 of the job. So you've done 1/7 of the job in 1 hour. Okay, now you'll begin to get the pattern on this. Okay, so that means this person in 1 hour has done 1/7 of the job. Does that make sense? That's the whole key to this problem, by the way. Okay, how about the next one? If you can do a job in 9 hours, how much of the job's done in 1 hour? Okay, now you see the pattern. Okay, so what you'll have on that is that will be 1/9 of the job. Okay, how about X? What's the pattern? What do you think would go here? 1 over X, exactly, for the same idea. Okay, so that would be the idea. Is you can think of this way: if it takes X hours to do one job, then what you can do on this, if you divided both sides by X, you would basically have 1 hour, that person's done 1 over X of the job. Okay, is that logical? Okay, now what we do is, let's go through and we're going to set up an equation. So the equation comes from here. We're just going to put these things together like this. So this is the equation you're going to have. These two people are working together. So that means if we add that fractional part of the job they're doing, that should be 1 over X. Okay, and that's because they're working together. That's the reason that you add those two like that. Okay, now what we're going to do is solve this, then we're going to check it and see if it's reasonable. Okay, so let me, before I solve this, let me ask you a question. Okay, let's say, for instance, that, okay, we know that if it takes one guy 7 hours and the other assistant 9, everybody agree when they work together the answer is going to be less than 7.
Yes.
How much less than 7, though? Let me ask it this way. What if it was 8 hours and 8 hours? The assistant and the guy can do it in the same amount of time. Then what would it be? 4, right? Okay, halfway in the middle. So it wouldn't quite be halfway in the middle, would it? Okay, it'd be off a little bit, but it'd be ballpark. It would be around a half. Okay, so maybe 3.5, 3.4, 3.6, we're going to find out. But it's important to know that when you work the problem out so you can make sense of your problem, see? Okay? So what we're going to do here is we're going to get rid of fractions like we've been working on. So the common denominator, if you do 7 times 9, you get 63. So can you tell me what you would multiply both sides of this equation by that would get rid of an x, a 9, and a 7 all at the same time? 63x. You got to get rid of an x, so you have to multiply it by an x. Good. So we're going to multiply that side by 63x, and we're going to multiply that side by 63x like that. Okay? You're going to end up with equations with fractions, so you get rid of those fractions. Okay. Well, let's write this out. We're doing a distributive property, so you'd have 63x over 1 times 1/7, and you're multiplying by that, so that's going to be 63x over 1 times 1/9. Then over here, you're going to have 1 over x times 63x. So hopefully when we do this, we're going to have a real simple equation to handle then, okay? What would be the value of what I just boxed in? What's 63 divided by 7? 9, okay. So you can cross cancel that. Okay, like that. That becomes 9, so that's 9x. How about 63x over 9? What's that? 7x. And then how about the right side? 63. Okay, everybody got that okay? We already learned how to do that. Okay, we've already done that kind of thing. So now let's solve the equation. So we would have 9x plus 7x equals 63. You can collect these like terms. That gives 16x equals 63. Okay, divide by 16. And then you would have x equals 63 over 16. Now you can do one of two things. You want to be able to use a decimal or a mixed number, okay? If you do a mixed number, you got to do a long division problem, okay? So 16 goes into 63 3 times. 3 times 16 is 48. And then if you subtracted that, I think you would have remainder of 15. So that means the answer is 3 and 15/16 hours. Or if you took your calculator and if you just did like this, if you did 63 divided by 16, then that'll be decimals that stop. So that would also be 3.9375 hours, like that. Okay, remember we kind of predicted that the answer would be somewhere around half of 7. Half of 7 is 3.5. So it's a little more than half. Okay, why is it more than half?
Because he's new.
Yeah, because the guy's a little slower. The assistant's a little slower, right? That's why. Okay. All right. So does that make sense to everybody? Okay.
Do you want to like round to 2 decimal places?
If you're doing like your homework on My Math Lab, just follow what they tell you to do. Sometimes they're going to want a mixed number, which is precise. Sometimes it'll be a decimal and you'll be told to round, like that. So that's the idea. Okay. So is it reasonable? Yeah. Okay. Somewhere about halfway in the middle. That's the idea. Okay. All right. Let's do one more. I'm going to let you do one. We're going to kind of do these in stages here. Okay. So this one says 1 pump can drain a pool in 6 minutes. Okay. So that would be like pump 1 by itself. That would be 6 minutes. So let's just kind of fill in what we have here. Okay, then this one says when a second pump is also used. Now you got to be careful about this. It says when you're also using the second pump, then that only takes 3 minutes. Okay, now you got to be careful about that 3. Would it go there or would it go there? How come? Why would it go in the bottom? Because it's both of them together. That's what it's really implying, is it says when the second pump is also used, then that's going to happen. Okay? And then what the question is how long would it take the second pump if it was the only one? So you got to read that carefully. Don't always assume any setup like the first problem. Does that make sense to everybody? Okay? Now, what part of the job is done? If it takes you 6 minutes to do one job, then how much of the job's done in 1 hour? 1/6, okay, like this. So you know that in 6 minutes you can complete one job, correct? If you divide both sides by 6, you get in one, that's supposed to say minute, that's not supposed to say hour, that's a typo. Okay? Yeah, I thought I was trying to trick you there, that's a typo. You could do it that way, but you'd have to do conversions, that was not the intention. So anyway, this is 1/6 of the job. This is what? 1 over x, part of the job. And then that's 1 over 3 of the job like that. So the setup on these problems is always the same, okay? Now, here's your equation right here. These two things add up to give you this, okay? So the things that are working together are the pump 1 alone and the pump 2 alone, and then that's equal to 1 over 3, like that, okay? All right, does that make sense to everybody? Okay, what are you going to do with this type of equation? What do you want to accomplish here? You want to get rid of fractions. What's the common denominator for 6 and 3? 6. Would 18 work? Yeah, 6 is easier. It just makes the arithmetic easier. Okay, so what I'm going to do is I'm going to multiply this side by 6x. I also got to get rid of an x. And I got to do the same thing to both sides. So I'm going to do that. Okay. All right, so let's just do a distributive property. So that's going to be, and see, you can multiply straight across if you want to. That's 6x over 6. And then this is 6x over x, like that. And then this side, if you want to multiply then reduce, you can. You can either cross cancel or you can multiply straight across. Okay, so what's left here? X plus 6 equals what? 2x. 6 over 3 is 2x. Okay? So that would be the equation that you could go through and solve then. Okay? Now, what I'm going to do is we need to get all the x's on one side. So you can move this x to this side. So you'd have 6 is equal to 2x minus x. The answer to that problem is x equals 6 minutes. Okay. Now, I want to see how many people, did anybody know what the answer to this was going to be anyway? Okay, that's a good question. Here's how I knew. What's the relationship between 3 and 6?
3.
That's half of 6, right? So therefore, it has to have the same number as that. So if it takes this pump 6 minutes and this one 6 minutes, then when they work together, they're going to cut the time of the job in half. Does that make sense? Okay, so I knew all along it was going to be 6. Okay? So that's something that you want to look for. You see what I mean? Okay, that's important. That's real helpful if you know that. Okay, so let's see. I'm going to give you guys about 5 to 10 minutes to work on the next 2 problems. I'll walk around and see if you're on the right track with this. I'll put this one up here. And then you can go ahead and start on that and see what you get. So you can keep working on the 30 if you're in the middle of it here, but this, let's see, the number 28, you had one person could do the job in 3, the other person in 5. Together is the unknown. Then you have 1/3 of the job, 1/5 of the job, and 1 over x of the job like that, okay? And your equation's always right here, so you would have 1/3 plus 1/5 equals 1 over x. I can see some of you struggling a little bit with common denominators. If you can't do something in your head, you can do 3 times 5 and get 15. That will work. It won't always give you the smallest one. So this one I'm going to multiply by 15x, both sides like that. Okay, if you multiply that straight across, that's 15x over 3. This is 15x over 5. And then this side is 15x over x like that. Okay? And if you write stuff out clearly, you're less likely to make mistakes. So that's 5x plus 3x is equal to 15. Okay? Then you have 8x equals 15. If you divide by 8, you have x equals 15 over 8. And that was what? 1.875. Okay? And then that would be in hours like that. Okay? And again, notice that half of 3 is 1.5. So your answer is going to be around half of that smaller number in the ballpark. That's how you use that for estimation. Okay? So I think everybody got that without any trouble. The next one we had, this pump can drain the pool in 12 minutes. But then it says when the second pump's also used, so the 7 minutes goes there, and then the question is how much for the second pump alone. So it goes like that, okay? And then what goes here is you would have 1/12 of the job, 1 over x of the job, and 1 over 7 of the job like that. So your equation you should have had was 1/12 plus 1 over x equals 1 over 7, okay? What's the common denominator of 12 times 7? What did you use? 84. Okay, so what I'm going to do is multiply both sides by 84x to get the equation put together. So what I do is this will be 84x over 12. This will be 84x over x. And then this last side will be 84x over 7 like that. So when you get rid of your fractions, you can use a calculator if you want to. That's 7x plus 84. I saw several of you missed that piece right there. And then this is 12x like that, okay? Now what you can do is move the 7 to the other side. So I'm going to just move that over to get 84 equals 12x minus 7x. So that's 84 equals 5x. And then divide by 5. And what did this one turn out to be? 16.8. So 84 divided by 5 was 16.8 minutes like that. Okay, so I think you guys did really well. I didn't see too many problems. If you follow this strategy with setting it up and the chart, it's pretty simple to do, but you want to understand that part of the job and what that means. Okay, that's the key. Okay, now on this next one, this one was just 3 wrappers. Well, not that kind of wrapper. That's like a musical wrapper. I think we're talking about gift wrappers here. So we'll say wrapper number 1, number 2, and number 3 like that. Okay, so here's what the problem says. It says that one guy can do this in 20 minutes alone, the next person 30 minutes, and 80. Okay, so the smallest number is 20. Half of 20 is 10. Did you end up getting somewhere around 10? You didn't? Okay, you got to be less than 10, or those other 2 assistants aren't providing help, right? So this would be, and this was supposed to be a minute, so you would have 1/20th of the job. That's how much that's done in 1 minute. 1/30th of the job is done by wrapper number 2, and 1/80th of the job is done there. Okay, then together you would have x minutes here, and then 1 over x like that. Okay, so that's the setup. And you guys seem like you have that down okay. So your equation is what? 1 over 20 plus 1 over 30 plus 1 over 80 is equal to 1 over x like that. Okay, now the next thing is, this is what I saw. Some of you were struggling to figure out the common denominator. Now there's different ways to do this. One way you could do this is the biggest number is 80. Okay, does 20 evenly go into 80? Yeah. Does 30 evenly go into 80? No, bad idea. Now go by 160. So I'm counting off by 80. If I go to 160, does 20 go into 160? Yeah. But does 30 go into 160? In fact, you could just look at 8 if you wanted to. But finally, if you go to 240, what happens? 20 goes in even, okay? 30 goes in even, and so does 80. So that's one way to do it, okay, without having to do factor trees and that kind of thing. So what you could do is multiply by 240x on both sides. Now see, if you multiplied 20 times 30 times 80, you would get something that would work for you, but it would be a much bigger number. So you want to always try to get that smallest common denominator. Okay, so when we do this, multiply, we're going to have 240x over 20. And then here we're going to have 240x over 30. And then 240x over 80. And let's see, that needs to have an x there. So that would have been 240x over x like that. Okay? Well, let's see. What do you have here? You can cross the zeros out. So that would be 12x. You don't need a calculator. You don't have to have one to do this. Cross the zeros out. 24 divided by 3 is 8. Cross the zeros out. 24 over 8 is 3x like that, and then that side, the x's cross out, leaving you 240. Okay? Does that look good? Okay? Add the like terms. 12, 8, and 3 adds up to 23x. That's equal to 240. So if you got down to that point, you probably got the right answer. So now I could divide by 23. Again, our answer should be around half of 20. So let's see what we get here. 240. Why am I doing that? Divide by 23. There we go. So let's see what we got. Look at that, 10 point something. See? You're always going to have a good estimation. So when you're doing homework, think about your answer. Okay, are you going to do that? Students always say yes, and they never do. Yeah, think about it. That's the whole key. You can tell if you're right on this problem, or at least tell if you're on the right track. So you would get x is equal to about 10.4 minutes is approximately what you would have on that problem. Okay? All right, does that make sense to everybody? Okay, I want to show you one more thing on this, then we're going to go ahead and do a break. If you were doing a mixed number, because sometimes students don't know how to do that, and remember this in this class, it's easy to get a decimal because you press buttons on your calculator, but if you want to do a mixed number, you just do this division problem. So 23 divides into 24 one time. 1 times 23 is 23. 1 left over. Bring down the next number. Okay, 23 is bigger than 10, so a 0 goes there. Okay, so what you would have is the answer would be 10 and 10 over 23 minutes like that. So do a long division problem when you need to. Okay? All right, so what do you think of these problems? Look like we did well. These are not that bad. So let's take a break till, what time is it right now? 1 o'clock. Come back at 1 o'clock. And then we'll finish this up. We'll do probably the part of the assignment that's a little bit harder. Last round that we did. So these are going to go back to having distance, rate, and time in it. Remember those? We did some. Okay. Well, let's write down the formula first of all, because that's real important in this. And one of the things that you do in the word problems that's a little bit different what you did on this is usually something's going to be the same. You're always going to either have the same time, same distance, or even the same rate. Okay, so that's what's going to happen on really every problem I'm doing is something's going to be the same. And one of the things you got to be able to do is rearrange this formula like this. So before I do this problem, let me just remind you, like if you took this formula and if you wanted to solve this for r, well, what would you do? You would divide by t. So you would get r is equal to distance over time. Okay, you got to be able to rearrange this formula. So you can write it that way. You can write it as r equals d over t, or you could even solve it for time. If you solved it for time, you would divide by r, so you would get d over r. Well, you got to memorize that one. You don't have to memorize the other two. You algebraically derive those, see? Okay? So what we're going to do on this problem, we're going to make a chart out kind of like what we did before. This problem is similar to something we did earlier in the semester, but it's not identical. All right, so this problem says that a boat is going 7 kilometers upstream. That's a distance in the same amount of time. Remember I said something's the same. What's the same on this problem? Time is the same. That's going to give you a method for how you're going to solve this. And then it's going to move 20 kilometers downstream. And then it gives the rate of the current like that. So let's make a chart. Let's have like upstream and then a row for downstream like we did earlier in the semester. And let's have a column for distance, a column for rate, and a column for time. Okay, we got to do this because we got to organize all of our information correctly. Okay, so let's see what we have. The first thing that we have is a boat is moving 7 kilometers upstream. What is that 7? That's a distance, right? So we're going to fill in that distance upstream is 7 kilometers. Okay, then it says it's moving 20 kilometers downstream. So that's a distance, so we have that. So the distances are different, okay, like this, okay? but it does say the times are the same. We don't know the times. It doesn't tell you what the times are, but since they're the same, that allows us to use the same variable. Okay, T and T, they're both the same. All right. Now, what we learned how to do earlier in the semester is, remember, there's two things going on here. You got to have the rate of the boat, and you got to have the rate of the current. If you're going upstream, that's going against the current. What does that do to the boat? Does it make it go slower or faster? Slower. So what you'll have is they gave you the current is 9. So remember, if you're going upstream, you're doing the boat minus the current. But if you're going downstream, what does the current do? It makes you go faster. So that would be B plus C. Now, we know what C is. C is 9. They gave you that. That's different. When we did these problems early in the semester, we didn't do that. So what I'm going to have here is B minus 9. Then I'm going to have B plus 9 there. So that's the first key to these problems, is getting all that information set up. You were given these distances. The reason you weren't given the time, but it said they were the same. That's the reason that we have that, T and T. And like I said, in these problems, something's going to be the same. Okay? Then that is slower, B minus 9. That makes the boat go faster. That's B plus 9. All right, does that make sense to everybody? Okay? Okay. Now, what we did early in the semester, don't write this down. I want you to just pay attention to this. What you guys did early in the semester is you did distance equals rate times time. Don't write this down because you're not going to do the problem this way. Okay, then you solved the system of equations by substitution or elimination. You do not want to do it that way because it'd be too complicated. Okay, so don't go there. Instead, what you want to do, and you want to write this down, is you want to write down the formula D equals rate times time. Now, what's the same? T is the same, so solve that equation for T. So when we set up the equation, we're going to take advantage of the fact that these two things are the same. So what I'm going to do is I'm going to divide both sides by R, so I get time is equal to distance over rate, like that, okay? Now we're going to set up our two equations, but we're going to do it this way. If you look at the first row, what we're going to say is we're going to say time is equal to distance over rate. Distance is 7, rate is B minus 9. Okay, that's what time is. You take the distance you travel, divide by the rate, and you get the amount of time. Okay, that would be that. The second equation would be the same idea. What would you have? Time equals what? 20 over B plus 9. Whatever's the same, you want to solve that formula for that. Now, those things are equal, so you can set them equal. We can do a substitution method. So we can take that, and we can plug that in for T, so we would get the equation 7 over B minus 9 is equal to 20 over B plus 9. And then we could solve that for B, and we'd have the speed of the boat. Okay? Does that make sense? Okay, whatever's the same, that's what you want to solve the formula for. That's what's a little bit different on this. Now, problem like this is a proportion. Remember, when we have two fractions are equal, you can just cross multiply. The other thing you could do is you have an equation, if you want to get rid of a B minus 9 and a B plus 9, you could multiply by B minus 9, B plus 9 to get one of them to cancel. It's your call. You can either cross multiply it or you can do it that way. Okay? All right? So let's just cross multiply this. So that's going to be 7 times B plus 9. Go this way, that's going to be equals 20 times B minus 9 like that. Okay, so that's going to give that to you. Okay? Got an equation? You can solve this. Do a distributive property. Go ahead and do that. So you're going to have 7B plus 63. Go to this side. You're going to have 20B minus 180. Okay, now it's your decision on which side to put B on. So what I'm going to do is just kind of rearrange it this way. I'm going to do this, and this is just a decision that I'm making. I'm going to move the 20 there, and I'm going to move the 63 there. Okay, at this level of class, if you're not already used to it, start moving stuff. Okay, it's less step writing, so you'd have 7B minus 20B is equal to negative 180 minus 63. Remember, if I move something from one side to the other, the sign changes. We've been doing that all semester. So 7 minus 20 is negative 13b. Negative 180 minus 63 is negative 243. Okay, then I can divide both sides by negative 13. I can take my calculator and see what we get. Sometimes they'll turn out to have decimals, sometimes they'll be whole numbers. But the two negatives do divide out. So we got 243 divided by 13, and that will give about, and I'll just round this to two decimals, let's just say 18.69 would be what the speed of the boat is if there was no current. So that would be the idea. Okay? So that would be the answer to the problem. Now the next thing I'm going to show you on this a little bit is because you want to learn how to do this. You want to learn how to check and make sense of your answer. Okay? I mean, that's meaningless. You just get an answer. How do you know it's right? Okay? You want to make sense of this. So what you can do on this is you can basically check like this. And I'll show you kind of how this goes now. What I'm going to do is I'm going to redraw. I'll have you redraw the chart. We don't quite know everything yet, but we're pretty close. Okay? We can figure this out as we go. Okay, so let's do this and see if this makes sense to you. Let's redraw the chart, upstream, downstream, distance, rate, time. Okay, here's what we know now. You were given that the distances were 7 kilometers and 20 kilometers. That was a given. Okay, what you just found was the speed of the boat. So what you could do is you could do 18.69 minus 9. Okay, and we'll do that on the calculator. Then we're going to do like 18. I'll zoom on this a little bit because I'm writing kind of small. Then I'm going to do 18.69 plus 9 like that. Okay? So if I was to do this, you know, if you need to use your calculator, you certainly can. So when you're going upstream, the speed of the boat without current is 18.69. But if you subtract off the current of 9, the boat is slowing down because of the current to 9.69. Okay? Now, what we have on this is if we do the next one, 18.69 plus 9, that's 27.69 like that. Now, here's how you tell you're right on this problem. Okay, the way you find time is you do distance divided by rate. Okay, so I'm going to do this now on my calculator. I'm going to do 7 kilometers here divided by 9.69, and I'll record that. Okay, and that's going to give about, I'll just use two decimals, 0.72 approximately. Okay, now let's do the next row. If I do 20 divided by 27.69, I get 0.72. Can you tell me why this problem is, why the answer is right now? Because the times are the same. Isn't that what the problem said? Okay, so they're the same. If they didn't turn out to be the same, then we obviously messed this thing up. Okay, so that's the idea. So the times were the same, so you're verifying that they are the same. That's the idea. Does that make any sense? Okay, these problems are kind of challenging to do unless you follow precisely what I'm trying to teach you. Something's going to be the same on these problems always. That's the key. Okay, all right, let's move on and do this next one here and see what we got going on here. Okay, so this one, it says a cyclist can bike at a constant speed. That's a rate, okay, for 15 miles per hour. It says he then returns home at the same speed. Ah, there we go. Remember I said something's the same, right? That's key. Okay, takes a different route. So the return trip takes 1 hour longer and is 20 miles. Okay, so the only way that I get through these problems is to make a chart up because that helps me organize my information. Just like the last problem we had upstream, downstream, well, this one, it's two trips. Okay, he's going somewhere, he's going to a place, and then he's returning. Okay, that's what's going on. Okay, and then let's have distance, and let's have rate, and let's have time. And let's put it together. Okay, so basically it says the cyclist is going at a constant speed for 15 miles when you're going somewhere. Now, what's 15 miles? A distance, rate, or a time? That's a distance, so that's 15 miles. We know that. Okay. Then it says when he returns, it's 20 miles. So we got that, okay? Then it said the rates were the same. It doesn't give you the rates, but they're the same, so what variable could you do there? You could use R for both, right? Okay, so we know that, whatever's the same. Okay, now the times, you got to watch the times like this. You don't know the times, but what you do know is the return trip took 1 hour longer, right? So you can do this one of two ways. You could just call that T if you want to, because you don't know it. So what would be 1 hour longer than T? T plus 1. Okay, so it goes like that. Now we got it. Now you could also do it backwards. You could say T and T minus 1. Would that make sense? If one time is longer, then the other one's 1 hour less, right? You could do it either way. So we've got everything put together in this problem now, okay? Now, whatever is the same is what you want to work with your formula on. So do it this way. Start by doing this. Go ahead and write down the formula, distance equals rate times time. So since the rate is the same, that means we're going to solve this formula for R. So how do you get R by itself on that formula? Divide by T, right? So you're going to divide both sides of this formula by T to get R equals D over T like that. Okay? Everybody with me okay? Okay. Now we're going to get our equations. But when we get our equations, we're going to do D over T. So it's going to go like this. The first equation is going to be R equals 15 over T. Okay, that's what that's going to be. That's your first equation. The second equation, what's it going to be? R equals what? 20 over T plus 1, right? Because you're doing D over T. These things are equal to each other. So it's kind of like doing a system of equations by substitution. You just set them equal to each other. So what you would have is you would have the equation 15 over T is equal to 20 over T plus 1. Then that is a proportion. You're going to end up with proportions on these problems, so you can just cross multiply, okay, to get this figured out then. And then that'll give you what T is, and then we can figure out what we're supposed to do is find the speed, but that will be very easy to do. Okay, so let's cross multiply this. So you're going to have 15 times T plus 1. Then go this way, you're going to have 20 times T like that. And I'll move this over here, and then we'll kind of finish this up. Okay? All right. So now, distributive property. Go ahead and do that. So that's going to be 15T plus 15. When you do that, equals 20T. Now decide which side you want to get the variables on, the T's on. So I'm just going to move the 15T there to get 15 equals 20T minus 15T. So that's going to be 15 equals 5T. Well, what's T in your head? 3, right? Okay. So we got the time on that is equal to 3. Now what that is that's this time, right? So if this time is 3, what is that time? 4, okay? Now what we're going to do is we're going to go ahead and get the answer to this problem and check at the same time. So we got T is equal to 3. So let's go ahead and kind of do this now. So, and you'll be able to do this in your head. So I'm going to just check and see if we're on the right track with this. So we have the trip going to, we have the trip going return, we have distance, rate, and time. Okay, the distances were 15 and 20. That was a given. Okay, what did we just find? We just found this distance was 3. So what did we say the other distance was? How come it's 4? Because the problem said 1 hour longer, right? Okay. Now, you guys already know, I think, that distance is equal to rate times time, right? So what would have to go there? A 5, right? 5 times 3 is 15. What if you put a 5 there? Would that work? 5 times 4 is 20. What did the problem say? The rates were the same. So see, I'm kind of checking and getting the answer all at the same time. Okay, so see, all you got to do to get the rate is you can take either one of these formulas right here. Just take R is equal to 15 over T. Well, T turned out to be 3, so 15 over 3 is 5. So that means that's 5, That's also 5. So the answer to the problem is the speed is 5 miles per hour. That's it. And it checked at the same time. Does that make sense to everybody? The rates are the same. Verify that whatever's supposed to be the same is the same. That's how you do the problem. Okay, what do you think? Do not deviate from the methodology I'm teaching you here. You'll run into some serious difficulties. Like I said, something's always the same. Whatever it is, that will tell you how to set the problem up. Okay? All right, any questions about that? Okay, this is just kind of teaching you how to organize your thinking. Okay, this one, what we're going to do on this one, I think, is identical to one that we did before in class. I'm going to go ahead and just do these with you together so we can get through this. So with this one, let's go ahead and let's start with a chart on this. And let's see what we're going to have. We have distance, rate, and time. Okay, this one says that you can fly from city A to city B in 3 hours with the wind and make the return trip in 7 hours against the wind. This is very similar. This may actually be exactly the same as what we did before earlier in the semester. So we're going to have a row for with the wind and a row for against the wind. Okay? So here's what it says. It says the trip is 714 miles, but then it says you can make the return trip, which means it's the same trip. So what would that tell you? Same distance. That's what's the same in this problem. But I also gave it to you. So this problem is going to go back in time to what we did several weeks ago. Okay, the rates go like this. So what you would end up having on this is it only says this. If you're going with the wind, that took 3 hours. But if you were going against the wind, you're going a little slower. So that's 7, like that. Okay. Well, what goes here? There's 2 variables. So what you're going to have is you're going to have the speed of the plane, which I'm going to call P. And if you're going with the wind, does the wind make this plane go faster or slower? So what are you going to do here? If W is the wind, what do you put there? P plus W, right? How about against the wind? What would it be? Makes you go slower. So that's P minus W like that, okay? All right. Now see, this problem right here is we can go ahead on this and just set up our system like this. This is like what we did earlier in the semester. So we could have 714 is equal to rate times time, because that will be an easy system to solve. We can do that. And then we're going to take this equation. Again, we're doing distance equals rate times time. You want to be solved for D, and we are already with that formula. So you'd have 714 equals P minus W times 7. So you got 2 choices. The best thing to do probably right here is take your calculator and see if 714 divided by 3 comes out even. And then see if 714 divided by 7 does. Yes? What's that? Now we have 2 unknowns. You're trying to find the speed of the wind, but you have to know 2 things. These problems are always going to have 2 unknowns in it. You don't know the speed of the plane. You also don't know the speed of the wind. And you couldn't figure out the speed of the wind unless you knew something about the speed of the plane. That's why you got to do that. Okay, so let me do my calculator and see if this works out. I always like to do it this way because if they turn out to be whole numbers, it's a little easier. So if I divide by 3, that'll give me a whole number. And if I do 714 divided by 7, that also works out. A lot of times these problems are designed that way to make it simple. So I'm going to divide that by 3, then I'm going to divide that by 7. Okay, this is the same stuff that we did earlier in the semester. So 714 over 3 was 238. The 3's would cross out, leaving you P plus W. Okay, 714 over 7 was 102. The 7's cross out, leaving you P minus W. Now what we're going to do is solve that by elimination. See, the W's eliminate, don't they? Right? So I just took my calculator and divided both sides of this equation by 3 and this one by 7. So add this up. The most common mistake students make on this is, what is P plus P? It's not P to the second, it's 2P. 1 plus 1 is 2, right? And then you can add this, so that would be 238, 438, that's 440, like that. Okay. 440. 340. See, I caught myself on that. So that's 340. Then I can divide by 2. And let's see, I think that would be 170. So you would get P is equal to 170, like that. Now you're supposed to find the speed of the wind. So you can take either equation in this system. Let's just take that equation right there. Okay? And if I do that, I'm going to have 238 is equal to the speed of the plane, which is 170, plus W. So I'm just taking that equation, plugging in the P because I know it now, right? Then I could subtract 170 from both sides. Then that would give me the speed of the wind. Okay, so that would be like, what is that, 58? Or is that 68? That's 68, isn't it? Okay, so you'd have 68 miles per hour would be the speed of the wind.
How did this become a subtraction problem? I didn't see that.
But okay, you're talking about this.
Yeah, over. Just, yeah, right there.
Right there?
Yeah, 170.
Okay, well what I did there is, okay, this is against the wind, so you're slowing down. That's why you have that. Now see what I did is we know distance equals rate times time. So I said distance equals rate times time. I divided by 7, that became P minus W. And then 714 divided by 7 was 102.
Right, and then, okay, so what?
So one of them's plus because that's with the wind, it's making the plane go faster.
I'm just surprised that they're going against each other in subtraction.
Oh, that's because it's an elimination. Okay, now what we're doing is once you get the two equations, we're doing elimination like we learned earlier in the semester.
Now I
Okay, that's the idea. Yeah.
Why do you recommend this equation for this?
What's that?
Why do you recommend this? Is there any equation for this?
No, it's just distance equals rate times time. And see what I've been trying to show you is something's always going to be the same. And this time the distance was the same. That's why I left it alone. Okay? If the rate was the same, then you solve for R. If the time's the same, you solve for T. If the distance is the same, don't change anything. You just go back in time the way we did this several weeks ago. That's the idea. Okay? All right. Let's do this these next two here to kind of finish this up here. Now let's see. This one, a little bit different on this one. Now this one says you have car A. Now I'm going to have you maybe draw a picture on this. This is a race. So car A says that it starts 1 mile behind car B. So let's say here's car B and it's going this way. And then car A is starting 1 mile behind. So I'm going to put a little picture to myself that, okay, that is 1 mile extra. Okay, so car A it has a distance that's 1 mile bigger. That's what you're going to get out of that part of the problem. Okay, then it says this, car A is traveling at 55 miles per hour. Car B is traveling 40 miles per hour. So let's stop there. Okay, will car A eventually catch up to car B? Yes, how come? Because it's going faster, okay? So it's going to happen eventually, okay? So now the question becomes, how long, meaning time, will it take for car A to catch car B? That's what the problem's saying, okay? So we're going to make a chart on this to kind of help us organize the information. Okay, let's see what we have. So we got two things. We're going to have a row for car A, because it has a different rate, has a different distance, okay, but something's the same. Then we have car B, distance, rate, and time. So what's happening is basically they're starting at the same time, but car B gets a head start. Is everybody clear on what the problem is saying? Okay, well, let's write down what we have. Well, it said car A had a rate of 55, car B had a rate of 40, so we have that. Okay, now this is kind of like, it's like a race. So they start at the same point in time. Guy goes and marks that go, shoots his gun, and eventually we stop as soon as car A catches that. So are the times the same or are they different? They're the same, right? Okay, they start at the same point in time and we're going to stop them as soon as they're right even with each other. So that's what's the same. You have to figure that out by understanding the problem. Okay, so we got that. Okay, Now the distances on this, we don't know the distance. You always got two unknowns in these problems. So what I'm going to do on this one is, you can do this one of two ways. I think a lot of times students might understand it better this way. Are these distances the same or are they different? Are you sure? They're different. How come? Because one car gets a head start. Which car travels further? Car A or car B? Car A. So how about if we call that D, then what would this be? Since it gets a 1 mile head start, what would it be? D plus 1. How about that? Okay?
Yeah, I think
Or did I do that backwards?
yeah.
No, let's see. Car A,
Doesn't car B get one?
no, car A goes further, doesn't it? So D and D plus 1. Now you could do this backwards. You could go D and D minus 1, if you're thinking that way. I'm just saying, the car A's got a longer way to go. It's going faster, right? Is that logical? Okay, either that way or D and D minus 1. It'll work either way. Okay, now what's the same? Time is the same. So the way you're going to solve this problem then is basically like this. You can say distance equals rate times time. So what we're going to do is we're going to solve for time. Whatever's the same, solve for it. So you want to divide by R. So you're going to end up with D over R is equal to T. Okay, now you're going to write your equations like this. So from the first row, you're going to have time equals distance, D plus 1 over rate, 55. That's equation number 1. You're doing distance over rate. What's equation number 2? Tell me what that is. D over 40, right? Okay, everybody with me on that? See, we're doing the same strategy on these problems over and over again. Whatever's the same. These things are now equal. So what you can do is you can plug that in there and you'll get the equation D plus 1 over 55 is equal to D over 40. And then you can cross multiply. And then that'll give us what, when we solve for D, we're going to have the distance of car B. Okay, so we're going to cross multiply. So that's going to be 40 times D plus 1 is equal to 55D like that. Solve the equation. Do a distributive property. That's going to be 40D plus 40 is equal to 55D. Decide which side you want the D's on. I'm just going to move the 40 here to get 40 equals 55D. And then I can divide by, whoops, why am I doing that? I'm way ahead of myself here. That needs to be 55D minus 40D. Okay, so that's going to be 40 equals 15D. Then you can divide by 15, and we can reduce that fraction, and we can even get a decimal if we want to. Let's just get a decimal on this and kind of see what we get. So 40 divided by 15, 2 points. Let's just, on this problem, round this to like 2.67, like that. Okay, so that's what you'd have. So if you look at what we just found, what is D? D is car B's distance, right? So that's 2.67. So what would that be? 3.67. So you're going to have 2.67, 3.67 there. And then we're going to go ahead and figure out the time and everything and check at the same time. Okay? So let's go ahead and put this together. Okay, let's see if this works out the right way. Let's see if we're on the right track here. So what I'm going to do when I check and verify is what we have is we now have this. Okay, we started off this problem. You were given the rates. That's what you were given. The times were the same. Okay, but we still don't know what the times are. So what we would have is 2.67 there, and then what's the other car? 3.67, because that's what the problem said. It's 1 hour longer. Okay. Now, how do you find a time? Time is distance divided by rate, right? So what's going to go here is we're going to do 3.67 divided by 55, and that's going to give the amount of time that this happens. So 3.67, I think this is in hours, and it's going to be a very small fractional time. So that's like 0.06, or let's say 0.067 is what that is. in an hour. This is a very fast race. Okay. Then what we're going to have going on here is if we do 2.67, and if we divide that by 40, what do we get? We got the same thing, roughly the same because we rounded. So see, we know we're right. Okay. So what will happen on this also is, now this is an hour, so you could multiply by 60 to change this to minutes. So if I just take this answer right here and multiply it by 60, then the answer of this problem would be like about 4 minutes, which is probably a best answer. Okay? If you're going from hours to minutes, just multiply by 60 because there's 60 minutes in an hour. So see, we know we're right, and now we got the time. Okay, does that make sense? Somewhat? Okay. These problems take a little bit of work and a little bit, you have to follow the procedure I'm showing you pretty directly on these, okay? Okay, I'm going to do this last problem, and then we're going to start with the next section. Next section's super easy. I mean, it's just like one of the easiest sections we do all semester. Okay, let's take a look at this one. Just do one more example. I'll kind of give you a lot of variety here. This says you got two automobiles are going in an opposite direction. A lot of times on these problems, I like to draw a picture. So they're going in an opposite direction. Okay, so we got that. Okay, and it says they leave at the same time. Okay, so something's the same. Okay, then it says one automobile is going 20 miles per hour faster than the other one. Okay, so we got that. So let's just say that this one is 20 miles per hour faster. It doesn't matter which one. That's your call. You can pick either one. So we got that. Okay, then it says in 5 hours, what's going to happen is they're going to be 650 miles apart. Now this problem's you're going to take a little bit different approach on this problem. So ultimately what's happening is in 5 hours, the distance between these two cars is going to be 650. And that's everything I've been given in the problem. They're going in opposite directions. They start at the same time. And in 5 hours, they're going to be that far apart. So what's the same? The time's the same. And the time's 5. That was given this time. Okay? And then the rates are different, but one of them's 20 faster than the other. Okay? Does you guys see what's going on so far? That's very important, is to understand, draw a picture if you need to figure this out. Now let's draw a picture. Let's draw our chart. Next thing is let's get everything organized. So we're going to have a row for car 1, and we're going to have a row for car 2, and we're going to have distance, rate, and we're going to have time, like that. Okay? All right. Well, what do we know? What is the one thing that we know for sure? The 5 hours, right? The times are the same. Without a doubt, those two things are 5. Okay? We don't know the rates, do we? But we know how the rates relate. What we decided was car 1 is going 20 faster than the other. So let's call that R. Then what would hold on, I'm doing that backwards. Doing this like this. Let's call that R. So what is car 1? R plus 20, because it's faster. Okay, like that. So that's how I do that. Okay? Now the distances. Now I'm going to take a totally different approach on this. Let me ask you a question. Do these two cars travel the same distance or different distances? One of them's going 20 faster than the other one. That's the whole key. They're going different. Which one's going to go further? Car 1, because it's faster, right? The faster you go, the further you go, right? Okay? So what I'm going to do on this, I'm going to take a totally different approach, and I'm going to say, hey, these distances are different, so I'm going to give them two different variables. I'm going to say D1 and I'm going to say D2 like that. Okay? Now I'm going to take a totally different approach. This is a little bit different problem. So what I'm going to do is I'm going to go ahead and just do distance equals rate times time. And then I'll show you how I put this together. There's another way you can do this, but I think you'll understand this way the best. At least that's my hope. Okay? So let's do distance equals rate times time. So you would have D1 equals rate, R plus 50, times 5.
You put
No, R plus 20, not 50. I don't know why I did that. Okay, so we're going to have R plus 20 there, right? Second equation, we're going to have distance, D2 equals rate, R times 5, like that, okay? Now here's what you want to make sure that you understand on this problem. Okay, here's what we got. This part right here, that would be the distance traveled by car 1. That would be D1, right? D2 would be this distance right here. They're two different distances. Now, can you tell me how D2, D1 relates to 650?
D1 plus D2 is 650.
What did you say?
D1 plus D2 equals 650.
Exactly. They add up to 650. They have to, right? Okay. This distance here and this distance have to add up to 650 because that's how far apart they are. So what you would get is this equation. D1 plus D2 is equal to 650, right? Does that make sense? It has to be. Can't be anything else. Okay. Those two distances are going to add up to that grand total. Okay. Well, what's D1? D1 is this. Okay. D2 is this. So your equation is going to be, D1 is going to be this thing I highlighted in yellow, so I'll write that as 5R plus 20, just putting the 5 on the other side. D2 is going to be 5R equals 650. Now see, that equation right there has one unknown in it. So I can solve it, and I can get the rate, and when I solve this, I'm going to get the rate of car 2. Okay, like that. Okay, so that's going to end up giving me, solve the equation, which is simple now. That was going to be 5R plus 100 plus 5R equals 650, like that. Like terms, so you got 5 and 5 is going to be 10R plus 100 is equal to 650, okay, like this. Okay, now I'm going to subtract 100 from both sides. So that's going to be 10R is equal to 550. Then I can divide by 10. So I get the rate of car 2 is going to be 55. They're obeying the speed limit. So that's 55 right there. Okay? All right. Now, what would the rate of car 1 be? 75. They're speeding. Okay, I guess, depending on what the speed limit is. Okay, we got that. Okay? Now, let's see if we're on the right track with this. Okay, the question on this problem was to find the speed of each. Well, we got the answers. We got 75 miles per hour and we got 55, right? Okay? What would you do to find D1? If you know the rate's 75 and the time's 5, what do you do to find D? You do rate times time, right? So you would do 75 times 5 to get that. So let's go ahead and do that while we're at it. Okay? So I'm going to kind of do a little check here as I go. So what I've got so far is I've got 75, 5, 55, and 5 like that. Now these distances are not the same because one guy's going faster than the other. So if I just do 75 times 5, I'm going to get 375. Okay, like that. And then if I do 55 times 5, the second other car is going to go 275. Now, we need to see why we're right. Any idea why I'm right? That's not why we're right. We already have that. The whole thing is, what's the deal with these numbers? What's supposed to happen to those numbers? There you go. They're supposed to add up to 650. So if you do 375 plus 275, you get 650. Do it on your calculator if you want to. That's why it's right. Okay? That's what the problem said, is those total distances are 650. All right, does that make any sense? Now, these problems can be a little challenging for students. The key is setting that equation up. And notice every time what I did was I did a chart. I drew a picture if I needed to, and tried to come up with an